स्टार्ट करें.
Yes.
Good afternoon. Myself, Dr. Praveen Thakur. I'll be taking today's lecture on the snow glacier mapping and monitoring using the synthetic aperture SAR data for this special course being organized by IRS under COs. So this is the outline of the presentation. First, the basics of snow and glacier hydrology and how we do the use of remote sensing with focus on micro remote sensing for snow mapping and monitoring, followed by glacier mapping and monitoring, including a few examples from the polar regions, and what are the future Earth observation missions which are focusing on these cryosphere components. So before we delve into the snow and glaciers, so these two are a subset of the cryosphere, which is also the frozen part of our planet Earth, which includes primarily the polar ice sheets in the North Pole, Greenland, in the South Pole, we have Antarctica, and the frozen sea is the floating sea ice. Broken part is the iceberg, and in the mountainous region, high altitude regions, we have the seasonal snow plus the mountain glacier, and then there is a big chunk of the frozen part is also permafrost, which is the frozen ground, and then seasonally we also have the lake and river ice. And this cryosphere constitutes almost 75% of the global fresh water, followed by the groundwater, and the surface water constituting only the minor 2% of the global system. So this, from the global perspective, again, it covers this 12.5% of planet Earth, and the glaciers covering 0.5% of the global area, and polar ice sheets covering the 10% and providing almost 70% of the Earth. And out of this, the fresh ice, the polar ice sheet component, it is 99% of the Earth's ice. And the sea ice and the snow cover, they are seasonal in nature depending upon which hemisphere, northern or southern hemisphere, and its value for the sea ice, it can vary from 3 to 4, from the minimum to 70 to 40 for Antarctica. Similarly, there is a variation in Arctic, and also in the snow cover, there is a variation of 3.8 to 46.5 million kilometers square from winter to summer time period, and also a significant amount constituted by the permafrost, which has again came into limelight due to the climate change and its potential of releasing the methane and the deadly viruses. And theoretically speaking, if this polar ice sheet is to melt, so it can cause significant amount of sea level rise, which correspond to almost 7 meter and 58 meter for polar ice sheets. And the challenges for us as Earth scientist is to connect the polar teleconnection with the mid latitudes, including Indian monsoon, how this global processes and feedbacks drives the changes in the polar sea ice, what are the properties which control the form and the flow of the polar ice sheet, how the glacier retreat and surge are and its governing factors and feedbacks are linked, and what are the volume and the elevation changes in these cryosphere components, including snow, glacier, and the ice sheets, and the changes in these components, for example, formation of the glacial lakes or decrease in the albedo, increase in the decrease in the freshwater flow can lead to the extreme weather events. And some of the priorities area of research in this field are to quantify the snowpack properties, providing the high resolution snow cover area, which feeds into the snow melt runoff model. What is the volumetric changes in the glacier elevation, how they are affecting the glacier health, and the changes in these components leading to disasters, for example, avalanche, icefall, rockfall, and the glof. And overall, if we see the basin wise, Himalayan river basin are generally fed by the snow and glacier. Any change in this can affect significant amount of population which lives in the downstream area, and also the extreme weather events, how these land surface processes are linked, and how we can better predict these extreme events, leading to the better flood forecasting. And on the global scale, what are the polar teleconnections with the latitudes? What is the polar sea ice variability, ice sheet dynamics, and the health of the ice shelf, which acts as a stoppage point for the free flow of ice into the oceans, and more importantly, the permafrost status and the dynamics. So these are the key areas. I may not touch all these parameters because for each of addressing these questions, you need a systematic observing system. And these frozen components mostly are found in the remote and accessible areas. And if you want to have the repeated coverage of measurement, which can give you the correct information about them, about their status volume, so we need to have the use of remote sensing. And how that is done, we use multiple satellites, imaging systems, which works in optical, thermal, or the microwave. And they have the different physical principles of reflectance or brightness, temperature, and the backscatter. And there is fundamental equations which governs the reflectance or the emission or the scattering properties. And fortunately, our scientific community, remote sensing community, have seen the progress in all the three domains, and we have the operational and some R&D based Earth observation satellites, which gives us the systematic coverage in all the three domains of the observing systems. And today we will focus more on the synthetic aperture radar, that is the active microwave component. Again, this is how we address from the passive active, which kind of component of the cryosphere we are addressing. And recently, one more type of gravity-based satellite, which gives us the total volumetric changes in the polar ice sheets and including the Himalayan glacier using the GRACE kind of satellites. So coming to the first part, we have the snow. So which is a typical hexagonal structure if you see in the microscope. And in India, generally in Himalayan region, we have the seasonal snow above 1800 or 2000-meter elevation. And in the higher latitudes in the northern hemisphere, even at sea level, you may get the snow cover. And this snow provides the important reservoir, which is the nature's way of storing the water in the winter. And then once the air temperature rises, the snow melt will be feeding into the various river basins. For example, in Himalaya, we have this Indus, Brahmaputra, and Ganga. And in the Alps and in northern America, we have the various river basin where we have a high dependency on the melt runoff coming from these snow-fed river basins. So this acts as a major source of water supply. And if you are living very near to the mountain, this dependence on the snow will be almost 90%. For example, in the Western United States or in the Indus or in the Chenab Basin in India. And apart from the this one, so agriculture, hydropower, and other ecological and environmental needs are fed by this snow. And sudden changes in the snow and melt can also sometimes lead to the floods. And on the global scale, because the snow is highly reflecting natural surface, so its albedo and thermal insulation on the ground, they provides the this feedback to the radiation energy and the moisture budget of the planetary scale. And sometimes we also call the this snow and the frozen ice component as the thermostat of planet Earth, which controls how our temperature is going to behave at the planetary scale. And just to give you the perspective from the Himalayan point of view, so this is the satellite-derived snow cover in the bottom picture, and above we have the satellite-derived inventory of the glaciers. So you can see the above one, it is the permanent ice reserves in form of glaciers, and the downstream, this area almost 10 times what we have in the glacier area in the peak, generally in the February and or early March. So this lot of area gets covered with the snow, and all our basins, major basins from Indus, Ganges, and Brahmaputra, they are fed by this snow. And this combined flow of these three rivers is almost 64% of the total water sources in India. And due to this snow availability, average yield also is higher. And this is just some of the examples. If you have the more area under the snow, you will have more contribution of the snow. For example, Chenab River has the highest 70%, followed by Satluj, and followed Ganga River as a 30%. And the snow does not remain the typical hexagonal structure that what we see in the fresh snow. It varies with the time, it varies with the density, it varies with the temperature. So depending upon the type and the presence of the water surrounding the ice crystals or the density of the snow, the reflectance properties as well as the emission and backscatter properties will change. And just to for the completeness, I will start with the optical, because in the optical it has a very high reflectance, and in the visible and NIR, and then there is a swirl of absorption bands in 1.52 and 2.5, and in the fresh snow we have the highest reflectance, followed by, as the grain size will increase, it will become wet. So the at near infrared you will have the absorption, and similarly for the fern also will have the less glacier ice, more less reflectance, and in the dirty glacier ice, which is the debris covered, it is the minimum. And this is just spectra to show, because we use this, especially the radiometric resolution. The older satellites, like the earlier Landsat and IRS series, they had the 8-bit data, so it used to get saturated. So the all the next generation Landsat and IRS, they have the 10-bit data, so there is no sensor saturation in the snow case. And generally these days we have the daily repeativity, and sometimes if daily is not available, 5 day and up to 16 days availability is also there. So depending upon the what basin area, how much frequently your snow is changing, so we select the appropriate sensor. And normalized difference snow index is the most popular method of deriving the operational snow cover, using the green minus swir band by green plus swir band and greater than zero point 0.4 plus additional values you give to avoid the open water bodies being classified as a snow pixels. And using this algorithm, some modification, there is a cloud free snow cover data has been generated. And even the satellite data product generators, for example, Modi's team, they have also recently come up with the cloud-free fractional snow cover. So you can see here in the long term, from the 2000 onwards, this snow cover change has been seen here, and for the northwestern Himalaya. And although there is no significant change on the overall, but if we see, there is a lot of annual variations. Sometimes there is a less snowfall, some years we have the high snowfall. So those variations are there. But if we compare from the 1980s, there is a, some significant decrease in the overall snow cover. So, but we do not want just the area of the snow. We want to quantify the volume of the snow. We want to know how much water is contained in the snow. So, for that, from the hyperspectral, we may get the grain size because of the reflectance change in the near infrared, zero point 0.9 to 1.9 micrometer. However, the other properties which defines the snow water equivalent are the density, depth, and other parameters, which are possible only using the microwave data. So there are two type of microwave. We have the passive microwave and active microwave. We will see how they behave. And from the optical, as I told, we do have the fractional snow cover area and the grain size, which is directly inferred from the reflectance properties. So once we have this grain size and albedo, there is an indirect way you can correlate it with the snow water equivalent or depth, but it is a qualitative, not the quantitative method of quantifying. And this data ultimately feeds into our land surface models, whether it is snow cover, snow water equivalent, or the moisture, so that our prediction of the water flow in the river system or in the watershed is improved. And also this data feeds into the various land surface models, which simulates the snow avalanches and other disasters. So for that also we need topography, high resolution topography, snow density, and initial snow depth. So all these parameters, if we can quantify accurately for the remote areas, our simulation accuracy of not just the snow melt runoff models, but for the hazard models also is going to increase. So just to complete the overall perspective from the microwave, I have included 2, 3 slides on the passive microwave. Here the emitted energy is gets less as compared to the emitted energy from the snow-free ground. And if you have the deeper snowpack, there will be less energy, shallow energy little higher, and highest brightness in the no snow condition. So the brightness temperature is the function of the this emissivity of the terrain as well as the kinetic temperature. So using this data, so almost 1970 onward from SSMI, passive microwave data is available at up to 25 kilometer. You can get the systematic daily snow coverage in terms of the snow occurrence, snow depth, and the snow water equivalent at the planetary scale. And these are the some of the frequencies where the changes in the various type of snow. For example, this is for wet snow, this is for the bottom crust snow. So depending upon what kind of snow we have the distinct change in the this emission signals. And the most popular and recognized signals are the 18 and the 36 gigahertz frequency, or 19 or the 37, depending upon whether we are using SSMI or AMSR kind of microwave radiometers. And using these two principles, not just the snow, but the sea ice variability has also been quantified from 1970s to till now. And this is just one of the formulas where we combine these two frequencies to derive the depth of the snow with corrections for forest cover and the shallow and the deep snow cover. And there is a global product, but it also has a certain limitation from the saturation point of view for the deep snowpack. And this is the example from the northern snow water equivalent, which is the multiplication of the snow depth and the density. And this is from SSMI at the global scale. This is from the AMSRE at the global scale. And why we say there is a saturation? Because if your snowpack is greater than 1 meter, and if your snow water equivalent is more than 150 millimeter, the brightness temperature is not sensitive beyond that. So there is a upper limit with traditional microwave remote sensing brightness temperature up to which you can get the snow water equivalents. So to overcome such issues, we switch our methods to the, this is one more example of for the polar studies. We switch our methods to the active microwave. Now, active microwave has a unique relationship with the snowpack. If it is a dry snowpack in the traditional microwave frequency of C band, X band, or L band, we call this as a virtually transparent. For example, if there is a C band and its frequency C 5.4 or wavelength also equivalent to that, and my snow grain size is in millimeters, and if it is dry, there is only ice component, there is no water component, so it is virtually transparent. So majority of the backscatter will come from the snow ground interface with very negligible volume scattering. And the reverse case may will happen in case of the wet snow, where we can see majority of the backscatter coming from the air snow interface, and very minor component coming from the volumetric component. So depending upon whether you are in peak winter season where you have all negative temperature, then it is the dry snow component. Our backscatter models will be different. And if you are in the melting season, our backscatter model or interferometric principle for measurement of the relative snow depth or the snow water equivalent will be different. And this is just one example how we see the snow or the glaciated areas in the optical image, and the same area in the radar images. This is the single polarization C band from the Indian RESAT 1 dataset. And if it is plain area, no issue. But for Himalayan region, it is generally we have this. Uh, just hold on. Yeah. So in the mountainous region, we have to select a typical incidence angle, ideal being the 40 to 45 degrees, so that we avoid the layover and shadow. And sometimes even at such incidence angle that may not be avoidable. So what we do, we combine ascending and descending passes to get the maximum coverage in the mountainous region to avoid layover, foreshortening, and the shadow aspects. And coming to the optical properties in the microwave, so we have the real and imaginary part and various frequencies. So you can see here the for the ice and for the water, it is almost reverse. So various microwave frequencies starting from L band to going up to Ku band. You can see it is almost near to the 1.75, 1.8, and for the water it is high. And similarly, imaginary part also it is less, very less as compared to the water portion. And generally, the permittivity, that is the dielectric constant of the snow, it is the direct function of the density of the snow. So this is the typical penetration depth in a dry snowpack, which is function of wavelength and the real and imaginary part of the dielectric constant. And if it is dry snow, you can see here there is a penetration depth from 5.3 to 36, minimum penetration in the Ku band. That is why it has the highest scattering component. And even at the X band, you have significant penetration in the dry snowpack. And this is the penetration depth exponential decrease, even your water content of 1%. So as I told, the real part is for pure ice is 3.15, and this is the density versus the real part of the dielectric constant for the snow, and this is for the imaginary part, and it is applicable for frequency from C band to L band. And similarly, for the wet snow, there is a one more component of volumetric water content. So using these two relationships, this is how we indirectly retrieve the density of the snow from the satellite data, because from the synthetic aperture radar data, we have the retrieval models, which will give us the dielectric constant of the wet snow as well as the dry snow. So these methods have been used. The first method that we use is for the wet snow cover mapping, because in the wet snow it will be almost darker appearance, and then if you can take the snow-free image reference backscatter data, so that can be used for mapping the wet snow cover. And then because this algorithm still may not work for all the terrains, for example, the forested area, so we mask out the forest and the layover shadow regions. But this is one of the methods which can give you the operational wet snow cover mapping. And the same has been earlier example was from the NVSat ASR. This is example from the reset one data from every 24 days in the this one for the Beas Basin. And similarly, this is for the Bhagirathi Basin up to Uttarkashi using the reset MRS datasets. And after that, we have one more publicly open data from the Sentinel-1 time series. So this is just a snapshot of VV-VH polarization. This is in the Dhauladhar Hills. You can see here, this is the melt season. So in the melt season, in the mountain tops, you can see there is a high melting, snow melt it is going on. And similarly, this is for the non-melting season during the February. The northern aspects still have the dry portion, this greenish color showing the high backscatter, whereas the southern slopes still have some melting snow. Similarly, in the this is for the upper Ganga basin. So the high mountains more than 4,000 meters, they have the dry snow, high backscatter, whereas the southern sloping slopes, which are exposed to the sun, snow is there, but it is under the wet condition, and this is for the single band image. So this data sets is now available in the Sentinel, so that can be used to automate the wet snow cover. So using those algorithms, this is one example for Beas and the Ganga basin, where we are estimating the wet and the dry snow. And before we go into the snow physical properties of density, wetness, and the snow water repellent and depth, so these are the some of the instruments, laser based or the microwave based, which are used to measure the depth of the snow. They are used to monitor the snow water equivalent and also snowfall as the water equivalent. So these are some of the two examples. One is working, other one has damage due to the heavy snowfall in the winter of 2019. And the basic principle using this is the we have this inversion models. I'm not going into the full mathematics. You can read the papers, published papers, and this inversion models ultimately will give us the dielectric constants. And then using the formulation shown in the previous slides, this dielectric constant is converted into the density and the wetness maps. So these are the some of the results for the Manali sub-basin of the Beas River Basin for the L band as well as using the C band radar data. And now we had reset Indian radar satellite. It has a hybrid polarimetric function because the previous algorithms they work on the dual polarization HHVV data. However, in the reset, we did not have the operational system of HHVV. Operational was HHHV, co-polarized, like the Sentinel, we have the VVVH, but it has the hybrid polarization. So we tested this for the hybrid polarization, and the algorithm has been developed to estimate the density using this hybrid polarimetric data. Similarly, for the wetness, we have used the method and compared it with the fully polarimetric radar set 2 data. Then both the methods are comparable with the slightly more improvement in the hybrid polarimetric data from the C band. Now, the other component which is very important from the water source management point of view is the total snow water equivalent, which is a function of the density multiplied by the depth. So we have this interferometric based methods where we have the snow and the non-snow component. So this change in the range due to the presence of the snow is the function of the refractive index. And if we remove all the topography and atmosphere and other noise from the phase. So this two-way phase difference in the differential interferometry can be correlated with the depth of the snow, that is delta Z, and the dielectric constants. And as we know, dielectric constant is the function of the density. So this entire formula can be reformulated in terms of the snow water equivalent. And if you see the theoretical modeling for a typical incidence angle and the density, so this can be replaced for the dielectric constant of 0.012, 0.05, and covering almost all the incidence angles less than 60 degree and all the densities. This phase difference from the differential interferometry can be converted into the delta change in the snow water equivalent with the function of incidence angle and the wavelength. So if this phase difference is accurate enough, so we can estimate the change in snow water equivalent as the density multiplied by the change in depth, what we have identified from this one. But this phase difference is very sensitive to the wavelength, and at the X band, for this phase difference to occur, it is almost at 18 millimeters. So this differential interferometry will work best for the L band, and recently we have the biomass SAR. So for the P band, it will have the highest possibility that higher values of the snow water equivalent can also be retrieved. So that I will show in the next slide. For example, here, so here the phase unwrapping almost snow water equivalent of near to 400 millimeters, whereas in the L band it is less than 100, and in the C band it is almost 80 millimeters or even less than that, and for the X band it is 18 millimeters. So the longer wavelength are much more suitable for this direct differential interferometry based methods to work. So this phase ambiguity is more in the L and C and the least in the P band. So the same method is converted into this, for example, differential pass, what I have shown. Then we can have the interferometric plus single pass, for example, from the tandem X kind of satellites. And then there is a fresh snow from the polarimetric phase. So if you are using the differential interferometry repeat pass and uh, the change in the snow cover or the depth. Despite that, there is a good coherence between the two dates. In that case, we can estimate this change in snow water equivalent, and direct phase difference can be correlated with the delta SWE. And this second principle will work on the same principle, but here what we are assuming, one date we have the snow free condition, and in the second date we have the full snow condition. So that happens in case of the wet snow. So if we are able to have good kind of coherence in these two images, then it can be used for wet snow depth estimation, but it is not possible to have the dry snow depth in this method. And then if you have the fresh snow between the two dates, and if you have the fully polarimetric interferometric data, so we can take the difference phase difference between VV and HH polarization because of the orientation of the snow particles. So one is horizontally oriented or randomly oriented, other is the vertically or horizontally oriented. So this VVHS phase difference is related with the fresh snow depth. And one of the earliest paper which quantified this multi-frequency snow from the CLC data, shuttle imaging radar working in C, X, and L band has given the retrieval model for density, depth, and the particle radius. And recently, using the TandemX pole InSAR data, we have tested these methods from the fresh snow depth as well as the standing snow depth for same Manali area where we have the good transport and 365 accessibility and field instrumentation. And this is the fresh snow water repellent, and this is the standing snow water repellent for the winter of 2016. And the shaded portions, because this algorithm will work for only for the open snow area, not the snow which is underlain by the forest area. So we have masked out that. And this is the histogram for the both. And as we discussed, Sentinel is available in a cloud platform. So this was the one of the first papers on the northern hemisphere, 2016 to 19. So this scattering index approach was used to estimate the depth of snow with some corrections for the fractional snow cover. And because this is a high value target, so sometimes if you need the daily snow water repellent or snow depth, so one method may not work. So this is one example where we use the machine learning, integrating the passive microwave brightness temperature backscatter from the C band, optical snow cover area, and the meteorological observations. And then these models have very high potential to give the operational snow depth and the water repellent. And in this, complementary to this is the KU band scatterometer, which using the SIRF algorithm has been generated at 2.25 kilometer resolution. And you can see a high backscatter even in the snow case. And this 1D radiative transfer model is used to estimate the weekly change in the snow water repellent. And similar products remains at the ISRO's Vedas website, where SCATSAT-1 based ice melt product is also available. So the second part we'll quickly cover is the glacier part. So glaciers are the moving rivers of ice, and they are found in the high latitude and altitude regions. And basically, we want to know the health of the glaciers, how much accumulation is happening, how much ablation is happening. And by observing this either from the optical data or optical data problem we have, until unless you go for the commercial remote sensing, sometimes there is a chance that you will miss the minimum snow that is found in the peak ablation season, because that minimum snow line is equated as equilibrium line altitude. So this is the same image. One is for 2020, one is for 2019. So in the September 2019, you can see here there is a very lower portion we are seeing the snow, where it may be possible that we are misinterpreting the snow elevation line. And this is just a pictorial representation how these glaciers move in the system. And to avoid such under or overestimation of ELA, we use the synthetic aperture radar data, which give us the all weather capability, whether it is the winter season or whether it is the monsoon season. And the most popular method of identifying of this glacier faces, which give us indirectly the snow equilibrium line altitude, is the time series composite. So we have the typical polarization, red color for spring, green for the late summer, and blue for the winter. And using this composite, we define these radar zones where we have the glacier ice, then we have the wet snow zone, then we have percolation high backscatter zone, and then dry snow zone, which doesn't see melting throughout the days, 365 days. So in Himalayas, we do not have such dry snow zone, only the percolation frozen zone. Then we have wet snow zone and followed by the bare ice. So this line of bare ice and the wet snow zone with some uncertainty in the superimposed zone, we have the equilibrium line altitude. So this method has been tested to operationally to all the major glaciers, including Siachen, Gangotri, and Badashikri. with the error rate defined for multiple years. So this is the how we without and overcoming the limitations of the optical data. So this data glacier phases give us the ELA, and the same will be automated using the upcoming NISAR mission. And this is one more example from the NISAR, from reset data from our SAC colleagues of ISRO, where this is available in the Vedas portal. You can see the temporal changes in the glacier phases identified from the radar data. And the same way, we have also used the polarimetric data to quantify the blue ice area in the Antarctica region. And the second major application in the glaciers is the glacier velocity. And this is the standard procedure where we are removing all the phases, and only the line of sight of velocity will be taken. And if it is single pass data, then only ascendings, and then we have to convert this line of sight into glacier using this formulation with some errors. And the first earliest examples of glacier velocity using radar was done using the ERS-1 data tandem pairs with 1 day repeativity, which gave very beautiful results, followed by this 6 days where we have the Sentinel-1A, 1B in 2016-17, and now we have Sentinel-1 and 1C, which also have the good temporal interval. So 1 day is ideal, followed by 6 days. 12 days may not be ideal for all the glaciers. So using this limited 6 day data, we have done for all the major glaciers. However, for the compound glacier, there may be high chances of the error, especially for which we have not resolved the direction of the glaciers. So just to comparison with the optical, the branches here it is having high velocity, whereas in the single pass there is a error. So this ascending descending combination will be overcome with the NISAR data, where the final product will be combination of both ascending and descending, so that you get a proper two-dimensional, and sometimes the three-dimensional velocity also is feasible using feature tracking as well as using the interferometry. And the same has been applied here in the polar regions. You have more number of passes of Sentinel. So this ascending descending has been combined to give you the glacier velocity, which is again used for calculation of the ice flux calculation. And by using this ice flux and mass balance, we can quantify the health of the glaciers. And similarly, it is example of combining fast moving tide water glaciers using the feature tracking, where interferometry fails. And for the smaller glaciers where it is the medium level velocity, your interferograms are well defined. You can use slow or medium velocity using differential interferometry, and the feature tracking using the SAR data for fast moving glacier to give you a combined product. And the same approach is being used for the NISAR mission. And NISAR will be complementing the existing polar as well as the global ice velocity products. For example, these are the existing ice velocity from the measures project of NASA, where we are getting the systematic ice velocity from the both the polar ice sheets. And the same way, we are going to get the better resolution product for the from the NISAR. So these are the two missions. NISAR, by end of this month, we are positive that the launch will be there. And the cryosphere is one of the major components, where not just the velocity, but the R&D based snow, water repellent, permafrost, and all the components will be addressed. And in future, we also have one very exciting mission known as Crystal for the polar ice and the snow topography altimeter, which is similar to Cryosat 2 with more better improvement in the resolution. So these two will be the workhorse. And also I should mention this existing Sentinel, which has also contributed, and the biomass SAR. Although it is meant for the forest biomass, but the P band also can be used, especially for the snow water repellent and for the glacier dynamics, if the incidence angle and the other constraint are within the limits. So that is all from my side for today's lecture. Thank you. Janardhan, if you have any questions.
Sir, right now, no questions. sorry for I couldn't join so today's lecture. Hello everyone. So my name is Junpei. Sorry for I couldn't join so today's lecture. But from my side, so we would like to explain the case studies of how UN Spider, UN USA contribute on the SAR applications. So let me share my screen. So today's I'm going to explain case studies using InSAR technology application of InSAR for groundwater induced land subsidence. So the lecture in this session, we would like to understand about UN USA and the UN Spider, and then understand the mechanism of groundwater induced land subsidence and the application of InSAR for groundwater induced land subsidence. So let me just explain my backstory. I'm now working at the UN USA, United Nations Office for Outer Space Affairs, in a UN Spider team as a remote sensing specialist for the disaster management. My specialty is a synthetic aperture radar, so the radar satellite analysis. I have been working for the landslide monitoring with the World Bank in Nepal, and then land subsidence monitoring with JICA in Jakarta, and then Guatemala City, and then flooding analysis with DEM, digital elevation model using the foundation model, and then forest height estimation with ADB, Asian Developmental Bank, as an individual consultant in Indonesia. And then you might be familiar to these words, Tomosa and then Polsa using rainforest and then unit to estimate forest height and then above ground biomass. And then also recently, I'm now stepping the digital twin world. So Tonga Preparedness Pilot Project for sea level rise simulations. So the first session is about UN USA, UN Spider. So just to make it easy to understand, I'd like to show you this video for the what is UN Spider.
Space is vital for saving lives, responding to emergencies and natural disasters, and achieving the Sustainable Development Goals. We wouldn't know there is a global climate crisis without communications and Earth observation technologies. 26 out of the 55 essential climate variables can only be monitored using space technology. The United Nations Office for Outer Space Affairs supports countries to leverage space technology and data. In 2006, nations established the UN Platform for Space-Based Information for Disaster Management and Emergency Response. We coordinate with a network of over 30 regional support offices across the globe to deliver targeted capacity building services. In 2023 and 2024, UN Spider conducted institutional strengthening missions in Nigeria, Algeria, Chile, and Ecuador. This led to the activation of the International Disaster Charter, saving lives during flooding and forest fires. Check out our knowledge portal for more information on UN Spider's work.
So as you can see, so UN Spider, so UN USA, expanding more like space science and technology. So for now, so what is UN USA? So United Nations Office for Outer Space Affairs. So main activities is to maintain the UN space registry and then share space information with member states and then enhance global development by improving space science and technology use, and then provide technical advice and then training on various space-related topics. So we established 1957, and also we are doing yearly base in the Congress. It's called COPAS, so Peaceful Space Science and Technology Use, and the space law or any other space-related topics. So it was started in 1967, and then already member state was grown up, and then 104 member states, and then now we are expanding more. And then our mission is a gateway, and then convener, and then also the capacity builder. And then using many like a space science and technology, communication, satellite, and then navigation, and then like a GPS and the GNSS, and then Earth observation for multiple applications, agriculture and the food security, and the weather forecasting, and the climate action, urban planning, and then disaster risk reduction, and then management, and the water management, and also water resource management as well. So UN-USA vision and the strategy 2024 to 2030, like here. So we are implementing a strategy based on the member states' priority. So space sustainability, climate action, and the SDGs, developing countries, and then stakeholder engagement. So our vision is super long, so I won't go detail, but so 5 key priorities, as I said, in that 5 pillars, we are focusing on Africa and then Latin America, especially. Of course, yeah, APAC is also our focal point, but in this strategy, we are very focusing on Africa and then Latin America. This is our organizational structure from the top director and then office of the director and the senior advisor on space science and education, right now vice director. And then UN Spider is focusing on the space science and technology for disaster risk management. And the ICG is aims to bring together all global navigation satellite system. And then also SAS, space application system, space application section. And then we are welcoming any kind of delegation from many countries, and then space agencies. And the CPLA team is also committee, policy, and then legal affairs, handling like a space law. So now focusing on the UN Spider topic. So UN Spider so stands for the very long name, and then our branch is also headquarters is Vienna, and then but we have an office in Bonn, Germany, and then Beijing, China. The mission is to provide universal access to all countries and then all relevant international and then regional organizations to all types of space-based information and then services for related to like a disaster management to support full disaster management cycle. We are doing 4 components: technical advisory support, capacity building, fostering cooperation, and then knowledge management. So UN-USA, as I said, so 104 member states, but the UN Spider only for the also very have been supported many space agencies like ESA and then NASA and the UK space agencies and then JAXA and then CNSA as well. So we call like regional support office. We are expanding more. So UN-USA organization chart. As I said, so director is Arti Framani. She spent over 25 years in telecom and then private sector side. And then Roland, my supervisor, is also have been working for the over almost 30 years experience in a United Nations system. So this disaster management cycle page was right is very important for our mission. So any kind of like a disaster management cycle includes like satellite data and then IoT or GNSS and then communication satellite component, and then also, of course, GIS stuff. So response, recovery, and then prevention, and then mitigation, and then preparedness. For each aspect, we are publishing using knowledge portal website how satellite data and then GIS technology for these phase, and then how contribute on that phase. So this is an example of activities in a UN Spider, so 2022. We call like a technical advisory missions, usually using 1 week. We are conducting training program for each countries based on the request. Then so in 2022, we went to the Armenia, Dominican Republic, and then Ghana, Nigeria, and then Paraguay, and the Philippines. Also, you can see right bottom, we are also cooperation body of the International Disaster Charter. which is also worldwide scheme for every not every, but the most of the space agency provides tasking satellite data observation images to the disaster countries and then project managers. So this is an example of activation flooding in Honduras. Also, I got many questions from many audience. What the difference UN Spider from other United Nations system? So this is a table for the GIS ecosystem in the United Nations. So as you can see, the UNGGIM, so UNGM and the UNGIS and UNGSC, and then many sector-specific geospatial applications, and then UN Maps volunteers, and then conference, and then UN Spider, and then UNOSAT. So this overview and then a description is a brief explaining the difference between each of us. The UN Spider is mainly a space-related activities, EO for disasters, and then space governance. So finally, we just touch on land subsidence. So today's case study sections. We are also doing analysis for the using SAR satellite data. So in this case, we just picked up Tonga Tapu Island Tonga. So this is not significant land subsidence affected countries and then island, but based on their request, I tried to do the analysis using Sentinel-1 data. And then for this analysis, I used gamma remote sensing. So it's, in other words, so that I used IPTA technology for multi-temporal INSAR analysis. So as you can see, not so significant by looking at only 6 months. It's not a huge land subsidence what happened in the island. But the Sentinel-1 has a C-band, so very sensitive to urban areas. So that's why also you can see any colored points showing time series data. So yes, I think you've already learned how multi-temporal INSAR analysis are very good for the analysis for the land subsidence and with the millimeter order. So okay, so the next example is the Guatemala City. In this case, I'm using MintPy. MintPy technology. So this is already published in our website, knowledge portal. So let me just try to click on our recommended practice and the user stories. So as you can see, so this is our knowledge portal website. We are frequently updating our website, and then as you can see, this is a user story for land subsidence monitoring by multi-temporal interferometric SAR analysis. In this case, as I said, so we are using MintPy technology or tool. Published by the Alaska Satellite Facility and then team. Maybe in this case, Guatemala City is also very significant. So facing a land subsidence issue, but not only Guatemala City, of course, the Indonesia, Jakarta, and then any other countries has the same problem for land subsidence. So Guatemala City doesn't have significant issue of the groundwater induced land subsidence. This is due to a more geological issue. But it also has very severe problem in the center part of city. So let me just zoom up, and then multi-temporal interferometric SAR analysis. I'm going to dive into more later, but the the usual workflow is so data collection and the interferogram generation and then multi-temporal processing and then deformation time series and the geocoding and then validation. So this is also Alaska Satellite Facility data search website. So you can get and then download any kind like a data in a open and free data. In this case, I downloaded Sentinel-1 data, and then as I said, so that we use like a MintPy software package. Maybe you can just click on the GitHub and then MintPy, and then of course you can use it. And then recently, like paid, we have to pay for this software or tools if you are also working at the private sectors. But the workflow is a very well designed in a MintPy time series analysis. So stack of unwrapped interferograms and the network modification, select reference point, unwrap error correction, network inversion. And then as you can see, so these like the flow. So it is also the open SAR lab ASF recipe book was already there in GitHub. So this is a Jupyter notebook browser or interface. So it's very easy to understand. So in the Jupyter notebook recipe book, and then install the software environment and then configure climate data store access and then access HYPE3 data and then load data with MintPy and then configure time series analysis and then perform the analysis and then run post time series workflows and then update your configuration and then reprocess the time series. That's a very simple workflow in the time series analysis. The results was here. So the southern part is more facing very severe RAM subsidence. And then also the over like 5 years time series, it has already like 100 more images it can provide the time series RAM subsidence, lambda subsidence graph. Also, by comparing magnet and then global GPS network map, University of Nevada, so GPS results, and then compare the INSAR analysis results, we can get a validation. So you can see no such a significant difference in SBAS analysis and then GNSS. SBAS maybe already, so the small baseline ones, but so I won't go detail, but the SBAS and the GNSS analysis result is get well aligned. So using this technology, so I hope so the countermeasures for any local government and the national government can take countermeasures. Okay, so from the next one, so what kinds like SAR data we are using? So this is a list of the free and commercial SAR data, synthetic aperture radar satellite data set. So the current free and paid SAR data and satellite data is flexibly so changed, but most datasets are paid by each country's space agency or private sector. So you can see in the right table, so the band XTL, this is the main sensor band areas, and the free and paid. Most of the X bands are not free, like a Terasa X and then Cosmos Climate and then CompSat, then Capella Umbra and the ISI Strix and then QPS. So including like a small satellite component, I think it might be paid dataset right now. And then C-band, the most famous satellite data is Sentinel-1. And then of course the older satellite like IIRS 1, 2, and then MBSat and then DataSat-1 also free. And then L-band is longer wavelengths, has like a more free and then open satellite data like so EROS 1 and then JERS 1 and then CSAT, and then nicer, so will be already so will be, I hope so, will be so the open published. And then paid one is AROS 2 sliding spotlight mode, and then also street map mode, and then Salcom Galfan 5, and then AROS 4 recently launched. It's gonna be so paid, but it's very so great ones. And then this is so free and commercial analysis tools. As I said, so we are using Gamma and then others imaging, and then also Sentinel-1 toolbox in the Snap. But many data analysis tools was there. So yeah, depending on the situations, and then any like so the your objectives, so that you can separately using these toolbox. Okay, so the next session is also understand the mechanism of the groundwater induced random subsidence. So what is random subsidence? Maybe some of you might be familiar to these topics. Random subsidence was a worldwide, so the facing so severe significant issue. It's mostly related to like a geological component, but yeah, in today's lecture, so I'm going to talk about so groundwater induced random subsidence. These are some of the examples, like overexploitation of groundwater induced random subsidence, Jakarta, Indonesia, and then Mexico City, Mexico, and then Arizona, so the USA. So this is a very famous articles, sinking city and the areas affected by random subsidence induced by groundwater withdrawal. So before jumping in the mechanism of groundwater induced random subsidence, I'm just telling you the hydrogeological properties of the aquifer. So in the aquifer, confined and then unconfined aquifers there. So unconfined aquifer, you can see the light figures, and then unconfined aquifer is directly connected to the atmosphere through the unsaturated zone. On the other hand, a confined aquifer is trapped between two impermeable layers. So that's why any people, so yeah, just digging out, and then also the constructing so the wells to the confined aquifer, because due to the recharging system, so different from the unconfined aquifer, using confined aquifer, so you can get yes, steadily like so yeah, you can get so anytime so they get water so by using the so recharging system. So yeah, so like so this is the water tables here, and then if you can get so the more water, groundwater from the well, this water table going down, and then yeah, at some point, yeah, this unconfined aquifers is running out, but the confined aquifer doesn't run out, even if the unconfined aquifers, yeah, in this level doesn't get any water tables. So this is why the confined aquifer, any people can during deep deeping down to the unconfined aquifers. So why does groundwater withdrawal cause subsidence? Removal of groundwater reduces pore pressures, and then aquifer materials compact under geostatic pressure. So this causes land to sink. So maybe as I said, so these areas are confined aquifer, and then aquitard, and then unconfined aquifer. Maybe if you can go drill down to the confined aquifer, and then get groundwater from there, and then usually so from the unconfined aquifer, so the just recharging through the aquitard, and then finally the random subsidence was happened from these these groundwater wells areas. So this is a very so great diagram how unconfined aquifer and then confined aquifer random subsidence, and then groundwater table, and then head and then stratigraphy, and then also groundwater basin. So groundwater head drops, and then effective stress increases, and then aquifer compaction, and then compaction may be elastic or inelastic. So groundwater system responds to discharge and then recharge in terms of changes in aquifer stratigraphy, groundwater head, and then groundwater system compaction, resulting in land subsidence for unconfined and then confined aquifer. So how do we model land subsidence? I won't go detail because this lecture is how InSAR technology can touch on the land subsidence analysis. But these 5 workflows, you can get information and then land subsidence model. So first one theoretical, and then semi-theoretical, and then empirical, and then influence function, and then artificial intelligence. So due to the source millimeter order scale, time series InSAR analysis is now working on monitoring by national government or any other international organization to monitor the land subsidence in each groundwater induced land subsidence countries. Okay, for the next session, the last session, so application of InSAR for groundwater induced land subsidence. So I think you already might familiar with what is time series InSAR analysis. There are many multi-temporal time series InSAR analysis like SBUS, PSI, Squeezer, IPTA, or any kind of tool and the analysis methods have a different components. So, but in this case, we are focusing on the general time series InSAR analysis. So this project was for Indonesia, Jakarta, so which is one of the global famous land subsidence facing issue the country is induced by the groundwater extraction. So land subsidence in Jakarta is predicted to aggregate widespread damage whenever a flood or a storm surge occurs. And then JICA, so Japanese International Cooperation Agency, is applying Japanese experience in dealing with the land subsidence in Tokyo to help Jakarta city bring the subsidence under control. You can see the left bottom. This is a mosque in Jakarta. It's a northern mosque, Jakarta area. So that sank into the sea after excessive groundwater pumping caused land subsidence. And then you can see the light figures. This is the outline of geology in DKI, which is the way of the saying Jakarta, so the prefecture. So it's totally different from the southern part and the northern part. It's a very different geological component. The northern part, looks like colored by the bluish ones. It's alluvium, and then the southern part is different components of mixing many different geological components. So, but due to the difference in the northern and the southern part, how sensitive to the groundwater induced land subsidence. So this project objective is to promote effective countermeasures against land subsidence in capital province of Jakarta through the implementation of pilot activities and the institutional capacity development. And then actual activity was conduct pilot initiatives to demonstrate land subsidence mitigation measures and then enhance the technical and the institutional capacity of relevant agencies in Jakarta for the formulation and the implementation of counter subsidence policies and then action plans. The target area is a very simple, specific capital region of Jakarta, mainly focusing on the northern part. We were facing severe land subsidence, but the southern part has another land subsidence issue, but that's why that we are expanding the southern part as well. So project period is so for around 4 years, May 2018 to the November 2022. So the 5 component tasks is data collection, analysis, and the monitoring system, and the menu of mitigation measures, and then investigation of damages and the risk, studying of adaptation measures, and then also awareness raising, and then planning, and the implementation committee action plan. When you planning like any INSAR analysis or not only like INSAR analysis, but the analysis tasks, you have to think about so the design and the planning, what kinds of like data we should use, and then processing, and then what approach, and then what kinds of like processing and the analysis methods we should use, and then also the outputs and then deliverables. We should be get well aligned to the end users' expectations, the outputs, and then deliverables. This is very important for the project history and then project management as well. So in this Jakarta land subsidence analysis use case, we are targeting, like as I said, 662 square kilometer for the DKI Jakarta, and then also the end user, the national government would like to understand what the historical period in the land subsidence has been happened, and then how much volume was subsided historically. So that's why we are using IIRS 1 and then IIRS 2, which is a great INSAR qualitatively great satellite data. And the next one is the processing and analysis, how to estimate land subsidence volume in such a older and historical period. Because right now, Sentinel-1 or any other data set could be like a sort of more recent, technically like so 10 years ago or so. So, but IIRS-1 has a more older period, or like a 2011 year of the observations. So that's why we picked up IIRS-1 and the IIRS-2. So mixing up INSAR and the SBUS and the accuracy evaluation with GPS and the leveling points. And then finally, we just we aligned with the expectation of the end user, national government, like a contour map for displacement and then time series graphs. So as I said, so the IIRS 1 has a more older observation archive data, so 2007 to the 2011. And then on the other hand, IIRS 2 was launched in 2014 and also it's now still ongoing. But so we have a gap period like 2012 to the 2013. So during this period, we just estimate the subsidence volume by calculating averaging the velocity of the land subsidence. So this is a content of the analysis approach, like a SAR interferometry and the accuracy evaluation. So 16-step phase images, it's a radian unit, and then displacement millimeter, and then displacement millimeter plus GPS. And then deliverables is very simple. So contour map for displacement, and then time series graphs, and then cross section, as you can see the right figures. And then output images is a IIRS 2 period, and the estimation period, and then also final IIRS 2 entire period. So maybe this diagram and then figure is already you are familiar to this one. But by using the phase difference, we are estimating like a land subsidence volume. And then, yeah, I won't go detail this one, like an equation topic. because the most important point how to approach the current actual use case, case studies. So as I said, by calculating a phase difference and then like a first observation and the second observation, third observation, and then statistically calculated, and then we finally get the information of how much volume in a historically random subsidence was happened. So, but we should also focus on the how to improve, like increase the quality. The step one is the call registration, and then also we get the initial interferogram and the simulation orbital and then terrain deformation, and then remove orbital and then terrain deformation, and then phase filtering and then noise filtering, and then phase unwrapping, and then convert phase to displacement. I think you've already learned these steps from the prior training, but we should, of course, decide which image and which date could be like a difference images. Also the which images are our slave images. So you might be very familiar to these equations. So yeah, we are jumping to how to get like this displacement volume, and how to get rid of these components by analysis and processing. At first, we have to simulate orbital and then terrain deformation using DEM, digital elevation model, and then orbital information. You can see the red colored ones, so the orbital deformation, and then terrain deformation, and the next one, so remove orbital and then terrain deformation from initial interferometric images. Then finally, we get the phase images here, and then the rest of the stuff is also the deformation, displacement deformation, and then atmospheric, and then noise phase. And then by reducing phase noise and the enhance the fringe, and then reduce the atmospheric noise by using the processing. I won't go details of how to get rid of the noise and then phase filtering, because we've already done. But finally we get the very clear images for the phase filtering here. And then finally unwrapping and then conversion to displacement. Maybe the current ones is the wrapped images, so the 0 to 360 degrees. And then we are estimating the unwrapped phase. So EROS2 is 11.8 centimeter. So by calculating the phase information, finally we can get the displacement volume here. So using the InSAR output here for each year difference, and then finally we can get the mixing up cumulative displacement volume. And then we got like a hotspots here, and the northern part is also where is a mosque, sinking mosque was there here, and then other areas has also some like displacement areas here. So we also created like a cumulative displacement time series and then cross section, and then you can see the EROS1 estimation and the EROS2. These are estimation period by calculating the velocity on the speed of the random subsidence, and then connected to the EROS1 and the EROS2 actual calculated analyze the volume of displacement, and then connected them, and then finally we got the total volume of displacement. So also we provided like a hotspots time series, and then volume of cumulative volume of random subsidence. And then we went to there, and then what kind of like a problem was there? The one example, like due to no sanction of the water or the the water from the area. There's not any compaction there. That's why the land subsidence was happened by building up the commercial building without any dewatering. And then finally, I'd like to explain a bit like a SBUS and PS INSAR analysis. But the time series analysis usually using multiple observation at the same location and in the same observation mode to perform interferometric SAR analysis, using all of the data in order to understand temporal changes. So yeah, of course, this Jakarta case, you can use SBUS or PS INSAR or any other multi-temporal SAR analysis method. But the most important point is how to qualitatively get good analysis results, and then which kind of satellite data we should use. And then finally, countermeasures for land subsidence is this example, establish monitoring structure, control volume groundwater, and then develop alternative water resources, increase the social awareness. These are very important components for how to countermeasure for the land subsidence. Alternative water resources could be we should find another water reservoirs and then developing a structure or distribution pipeline system and then distribute water system. But in Jakarta, historically, the groundwater could be more clear and then quality good compared to the water pipeline system. Yeah, because due to the less water pressure, and then yeah, people cannot use the water pipeline system historically. So that's why anyone creating the groundwater wells, and then more land subsidence was accelerated. And the increasing the social awareness is also important because people doesn't know how much land subsidence was happened. So yeah, these are just examples, but a very important point for how to countermeasure for the land subsidence. Okay, finally, so thank you so much. This is just a case study. And then, yeah, D is SBUS, PS INSAR, and then any kind of analysis, multi-temporal INSAR analysis was in the world. Yeah, but the United Nations and then my experience in Jakarta, it was very exciting. And then based on these results, national government and any stakeholders can understand how much land subsidence was historically happened, and then it was directly lead to the change so national policy. So it was so great technology, so INSAR analysis, multi-temporal analysis too. But of course, that's just analysis results, and it's not direct survey. So we should, of course, anytime always evaluate and then compare the ground level data and then data analysis results. Finally, yeah, we get aligned to the national level policy and then direction. Yeah, which way we should focus on the countermeasures. Okay, yeah, sorry for long talking, but I hope this lecture will work for your future careers and then your analysis specialist. Thanks.
Good afternoon, friends, or good morning in some parts of the world. In this session, I will be discussing on interferometric synthetic aperture radar for monitoring geological and mining hazards, essentially on mining-induced subsidence as well. Myself, R.S. Chatterjee. I am from Geosciences Department of Indian Institute of Remote Sensing, Indian Space Research Organization, India. Okay, so yeah, I'm changing the slide. Yeah, so interferometric synthetic aperture radar. So this other faculty have already discussed, but even then, I will just brush up that interferometrics are it is essentially based on this interference of SAR signals. Okay, and for that purpose, you need at least 2 SAR images, and so from this interference, we'll get this interferometric phase. That is the phase difference of 2 SAR image over the same area. And from this phase difference, we can get the path difference of the your spacecraft, 2 satellite, or 2 platforms that are. From this path difference, we can calculate what is the surface deformation the pixel might have suffered during this time interval. These 2 images are acquired. And if the 2 images are acquired at the same time, so there is no question of surface deformation. So in that case, it can also be used for some other purposes, like for getting a very precise this terrain topography, that is the digital elevation model. And sometimes these 2 images can be acquired with a shorter time interval. Let us say like in tandem mode for 1 day or 3 days or few days interval. So in that case, this the pixel correlation can also be used to understand that whether this land use land cover over this pixel, okay, how much it is temporally stable at the scattered level. So that can be used for some applications that I'll discuss in the next slide. So in interferometric SAR, in acronym InSAR, we obtained the product is the interprogram. And an interprogram, it is the image representation of pixel by pixel phase difference between 2 SAR images. And now see what is the unit of measure of this interprogram. It is a phase cycle. So a phase cycle, that means the 2 per radian phase difference. That is the unit of measure in interferometry, and that is known as a fringe. And this one phase cycle or one fringe, it represents certain height difference. When you use this for the purpose of getting a high precision digital elevation model, okay, this fringe height, that is the terrain elevation difference into the space difference. Okay, it is a function of a number of parameters. For example, this is the baseline between the 2 satellites. That is the spatial baseline. This is then your look angle of the radar beam. Then what is your orbit height? That is the range. Okay, along with the wavelength. But in the case of differential interferometry, where we are using this interferometric phase difference for the purpose of only land surface deformation, okay, here only this phase difference is a function of only the wavelength of the radar. And you know, this is 2 pi radian phase difference over 1 fringe. This in a difference interprogram that represents only lambda by 2 displacement along the line of sight of the radar. Okay, and you know lambda is in few centimeters only. For example, in case of C-band, it is 5.6 centimeter. So it will represent 5.6 upon 2. So 2.8 centimeter displacement. It will tell, one fringe will tell, okay, between the 2, your image acquisition dates. Now, let us see what are the different applications interferometrics are. As I was discussing in the previous slide, one of the important application is topographic mapping. You can get a very high precision digital elevation model. Okay, and here the digital elevation model, the precision is up to meters. In fact, few meters. I'll discuss what kind of this interferometry, what kind of data is required, or what kind of InSAR techniques should be adopted to get a very precise digital elevation model. Because there are certain applications, particularly in the mining areas, other than different other areas as well, there are applications. Okay, And the other application is from this interferometric SAR covariance. That is nothing but the correlation coefficient of the pixel at the scatterer level. But this correlation coefficient is the complex correlation coefficient. So it takes into account the amplitude of the radar wave as well as the phase of the radar wave. Okay. In fact, this this wave in totality, it calculates what is the this correlation between the two images at the pixel. And if the correlation coefficient is high, that means the pixel at the scatterer level is stable. And if the correlation coefficient is low, that means the pixel is not stable at the scatterer level. And depending on this stability of the scatterers on it, this time domain, we can use it for different applications. For example, land use land cover mapping, because there are certain land use land cover class where the scatterers are not temporally stable, like the dense vegetation or forest, or the water bodies, they are not temporally stable. But if you consider the settlements, the buildings, or the rock outcrops, here the scatterers are always stable. There is no change at the subpixel level. So in such cases, whatever be the temporal interval, okay, you will get the correlation at the very high correlation. Okay, and correlation coefficient will be very close to 1. Similarly, this correlation coefficient can be used for environmental monitoring that we will discuss, because there are certain environmental indicators, certain environmental parameters, okay, they are sensitive to the temporal decorrelation. For example, in case of mining, okay, in open cast mine, for example, if certain open cast mines, it remains abandoned, it remains closed for a long time, it will be waterlogged. There will be vegetation growth. Then that particular pixel in the open cast mines will not remain temporally stable at the scatterer level. But if these open cast mining operations are ongoing, then it is more or less stable, not very highly stable, but it is more or less stable. So in such cases, your correlation coefficient will be high. But in the other case, where the open cast mines remains abandoned for a long time, it gets waterlogged, vegetation growth happens. Here, this temporal stability at the scatterer level is very low and correlation coefficient is very low. Similarly, you can use it for coastal dynamics on the basis of shoreline change. And shoreline means it is the boundary between the water and the land. And water, because of its liquid state, it is not stable at the scatterer level, because always there are some kind of movements happens inside the pixel. Whereas in case of land, there is no movements. But if for long time interval, if you take 2 images, then in the land also, there may be some plants, there may be some trees, there may be sand, so they may not be temporally stable. But if the 2 images are acquired at a short time interval, let us say 1 day, then water is not stable, land is highly stable. So the shoreline, you can get very precise shoreline. Okay? And if you have the shoreline at different times, then you can get how the shoreline behaves with time. Maybe we'll discuss if time permits. Okay, it is not in the area of mining. So if time permits, we will discuss how these other areas of environmental monitoring. Most important areas of applications of interferometric SAR is for land surface displacement. You know why? Because it gives you this spatially continuous. For all the pixels, you have information about the land surface deformation. Unlike in case of this, your GNSS observation and the GPS observation, you have high precision, this your land surface displacement measurements you can do, but that is at that particular point. But in case of interferometric SAR, you can have this very high precision, sub-centimeter level precision of land surface displacement for all the pixels, almost all the pixels, may not be all, okay? Because there are some problem of this interferometric SAR coherence in some pixels, but almost all the pixels, it will give you spatially continuous land surface displacement. That is the reason why interferometric SAR, rather differential interferometric SAR, is so important, so popular to these geologists, to the geophysicists, to the environmental, the science people. Those are interested in working on these areas of land surface displacement due to earthquake, due to landslide, due to volcano, due to glacier, or due to land subsidence. Land subsidence can happen due to n number of reasons that maybe we'll discuss in the later part of this session. Now see, there are interferometric SAR. where these two images you can acquire at the same time. Also, you can have two images at some different times. Okay, so one image you take in day 1 by the satellite, another image you acquire day 2. There is a time interval. So if so, then, but there is no deformation. Let us assume for this area there is no deformation. So then in that case, after this interferometric processing, what you get? Interferometric phase. That is the phase difference between the two images at the pixel level, delta phi. So this delta phi is equal to what? This delta phi is equal to this horizontal contribution because of the horizontal distance difference between the pixels that will contribute the phase difference. Vertical distance difference between the pixels, that is the height difference between the pixels, that is the topographic phase, there's the vertical phase. And the other component is the noise. You can have also atmospheric phase if you take two images at different times, because atmospheric profile may not be the same at two different dates. And noise comes from the temporal decorrelation and spatial decorrelation other than thermal noise. Okay, so now in case of this interferometry where it is used for the topographic mapping or this high quality DEM, this mapping digital elevation model, in such cases we need to remove the horizontal phase. Okay, but in such cases what is important? We need to avoid this noise, temporal decorrelation noise. Okay, so to avoid this temporal decorrelation noise, what we can do, we can have both the images at the same time. If you have both the images at the same time, so then there is no temporal decorrelation problem, because one transmitting antenna is sending the radar pulse. After interaction with the terrain, with the Earth's surface, the radar pulse which is returning back to the receiving antenna. So from these two receiving antenna, you are receiving this return pulse and you have two images. So interaction happens once only, and there is no question of time difference. At the same time, two images are acquired, but these two images are acquired from two different positions of the satellite. Okay, so from the same platform, you can have these two receiving antenna at some distance, or maybe two satellite in formation. One is transmitting and both are receiving. That is also possible. This kind of configuration we'll discuss in the next slide. Okay, in the other case, let us assume there are some land surface displacement happens, maybe due to earthquake, maybe due to landslide, maybe volcano, maybe land subsidence, anything. Okay, now you have one image at day 1, another image in day 2. Okay, then this interferometric phase or this phase difference of these two images, one is before the event, another is after the event. It consists of horizontal phase, vertical phase, the deformation, the movement phase of the pixel, the atmospheric phase. Why? Because these two images are acquired always at two different times, and atmospheric profile are not the same for these two images. So because of the atmospheric profile difference due to the tropospheric difference in the troposphere and in the ionosphere, total electron content difference. Okay, in the troposphere because of essentially due to the this water vapor. Okay, so there will be differential atmospheric phase, and this atmosphere needs to be removed. Okay, and then noise. Now you see, in this case, you need to remove horizontal, vertical, that comes from this topography, horizontal from the orbit, then atmospheric phase and noise. If you remove all these components, what remains is the movement. Now you see, in case of this interferometry used for DEM generation, this precision of measure, the sigma h, is something like this. This is a function of lambda, and the rho, that is the range, loop angle, this theta, and most importantly, the baseline. This is the baseline. So longer the baseline, more accurate is the DEM. Why? Because this sigma h, the precision of measure, will become smaller, isn't it? Now, in this case, one fringe height is also known as the HA, altitude of ambiguity. Smaller is the HA, means more accurate is your DEM. Practically, it is about 1/20 to 1/40 of the fringe height or altitude of ambiguity, which comes around a few meters DEM precision. But in the case of differential interferometry, that is for land surface displacement, you see this is the precision of measure, sigma phi upon 2 pi into lambda by 2. And sigma pi is this uncertainty in the phase measure. It is not more than your 10 to 20 degrees. 10 to 20 degree. So how much you get? 10 to 20 degree by 360 degree into lambda by 2. It will be sub-centimeter level precision in few millimeters. Okay. If you use the shorter wavelength like X band or C band, maybe 1 millimeter or so. If you use the L band, then maybe it will go even up to 1 centimeter or a little more. So this is the precision of measure. Now see what I was telling you, that in case of interferometric SAR-based DM, we should always rely on the single pass interferometry. It is better. But when it is not available, then you have to use the repeat pass interferometry. Okay, but there are certain conditions we need to look into. I'm not going to that discussion. So in that case of single pass interferometry, there are two important missions we have. One is in 2000. This is Satellite Radar Topography mission. I believe that most of us are using almost regularly or daily. We are using this SRTM DM, digital elevation model. And this is this configuration. This is the transmitting this radar wave, green, and this is the return radar wave received by two receiving antenna here, one here and another here. And this is separated by a mast of 60 meters, 200 meters. So always the spatial baseline is same. So DM is always the normalized, isn't it? Spatial baseline does not vary for the different data pairs. It is all same for all the images, all the image pairs. But in case of SRTM, there are dual frequency, C band and X band. But X band does not cover the entire area, only 1/4 of the total area. Okay. But here in SRTM, we could achieve a near global this digital terrain elevation data of level 2 digital elevation data. Whereas in case of TerraSAR Tandem X, which was launched in 2007, TerraSAR X and Tandem X in 2011. Now see, two satellites are launched in such a way they are moving very nearby. Okay, so TerraSAR X and Tandem X information. So one satellite is sending the radar pulse. After interacting with the Earth surface, these return pulses are coming back and both the satellites are receiving. So you have two images at the same time by sending one radar pulse. And in case of this single pass interferometry, you can do. But here, what is important, it is all X band. TerraSAR Tandem X, all X band. It is not C band, X band. And in this case, we could achieve this high resolution, this terrain elevation data at the level 3 level. Level 3 and level 2. Level 3 is quite high precision, much higher than the level 2. So that is how different they are. You can see here, relative vertical accuracy in case of level 3 is it goes up to 2 meters. In case of slope, where slope is little higher, greater than 20%, then it is 4 meters. Okay, so 2 meter to 4 meter is the vertical accuracy. Level 3, whereas in case of SRTM level 2, this is 12 meter to 15 meter. And relative horizontal accuracy, you see, in this case, 3 meter and SRTM 15 meter. So now we have all level 2 and level 3 DM, isn't it? And this DM can be used for some of this mining related, these environmental applications that we'll discuss. Similarly, this interferometric SAR coherence is also very, very important in some of the mining related these applications and other environmental monitoring applications, as well as in case of coastal dynamics, land use cover mapping. Then what is InSAR coherence? InSAR coherence is the correlation coefficient between two SAR images in complex domain. And this is the formula like this. Okay, it is a quantitative measure directly related to the amount of noise present in the SAR interprogram. So from this value of the InSAR coherence, you can tell that whether that particular interprogram is of good quality, more signal, more information, or more noise. If the correlation coefficient value is high, that means this pixel gives you more your signal related to your path. Okay, radar path difference. Radar path difference is used for the elevation data, digital elevation modeling. It is also used for the land surface deformation studies. Okay, so interprogram quality is a function of this value of the InSAR coherence. That is the correlation coefficient. It's a measure of phase stability between two radar images, an indicator of the interprogram quality, The higher the coherence is, the better is the quality. But see, this, what it represents, essentially it represents the space with this temporal decorrelation property. A bit spatial decorrelation as well, due to the spatial baseline, but essentially the temporal decorrelation property of the scatterers in a pixel. And that can be meaningfully used to characterize land use, land cover of the pixel, scatterer stability of the pixel. And using this temporal decorrelation property of the scatterers in the pixels, this InSAR coherence can be used for environmental monitoring of mining areas, land degradation, coastal dynamics, many applications we can have. Just for mining area, maybe we can highlight, just see here, one of the these coal mines I have shown here. This is the Jharia coalfield. This one of the 54 Gondwana coalfields in India. Is one of the most important coalfields in India. Why? You know, it is because it hosts the prime quality coking coal. This is the only coalfield in India which hosts the prime quality coking coal. Okay, but unfortunately, this mining has been happened more than a century. Okay, and these damages are extensive. This is the worst affected in terms of the coal fire, in terms of the this land degradation, land subsidence. Okay. Now see, this is the false color composite image from the Indian satellite sensor LIS3 data, and this is 543, means it is the SWIR one, then near infrared and the red band RGB image, and this is the open cast mining area. And here, what we'll discuss mostly these your impacts are due to the open cast mining. This is the open cast mining area. You can see that. See, from this optical data, what we can do very nicely, that is the mapping of the open cast mines. That is the open cast quarries. But while you are going to map these overburden dumps or the coal dumps, there is problem. Particularly in case of overburden dumps, there is spectral overlapping with other land use land cover classes. For example, settlements, for the rock outcrops, we see river sand. Similarly, for the coal dump, there is a spectral overlap with the open cast mines itself. Okay, so then we are looking for some other kind of these approaches. So interferometry is one of this efficient technique where we can map these overburden dumps using the high precision digital elevation model and the spectral signature in the optical image. And the interferometrics are coherence, the correlation coefficient. It helps us to identify this your unreclaimed, abandoned, closed, abandoned or closed open cast mines. Okay, that you see here. For that purpose, what we need to do, we need to have two images at shorter time interval. For example, you can have these tandem image, although it is a very old image like IIRS1 and IIRS2, with a time difference of only 1 day. The similar images we can have now with a few days interval, like Sentinel-1, you have a time difference of this 12 days, but 1A, 1B, we had previously 6 days. So is a shorter time interval image if you can have, then it is more useful. So in this case, 1 day. So from that, we generated the phase difference or interprogram image, and this is the coherence image. That is the correlation coefficient image. Now you see from the interprogram, we generated this digital elevation model, and this quality is around 5 meter is the accuracy. That is RMSE tells us that at selected points. Now from that, we identified what is this low-lying areas, that is the open cast quarries, and what is the these elevated areas, that is the overburden dumps and the coal dumps. Now from these elevated areas, we have these possibilities, either overburden dumps or the coal dumps. Now that we have this demarcated using the optical spectral signatures, because in case of coal, the spectral signature is different, it's dark, and in case of overburden dumps made of sandstone and shale, okay, it is mostly bright. Sometimes carbonaceous shale and coal also mix. In such cases, it is little low. Now in case of interferometrics or coherence, no, the total open cast mines we could map from the optical data itself. But out of that, some of the open cast mines, those are remained unreclaimed for a long time, abandoned for a long time, or temporarily closed. So this kind of monitoring we could do from the interferometrics or coherence, because the open cast mines, those are closed or abandoned for some time, okay, abandoned permanently or closed temporarily for some time. For such cases, there are water logging happens because for open cast mines, the aquifer has been cut and water is accumulated there in the open cast mines. And if it is for a long time, sometimes even vegetation can also grow, but in general, very less. Now, see, in such cases, your decorrelation is very high, temporal decorrelation is very high. So coherence level is very, very low. You can see here coherence is very low in some of the areas, including these water bodies like river water or lake waters. That also it includes that we have to mask it out. Out of that, so we can map very nicely what are the closed mines, unreclaimed abandoned mines, what are the coal washeries, and what is the open cast mining area or project area where the mining is ongoing, is happening now. So this kind of this information you can derive from interferometric SAR, and that you can combine together, okay, from optical image, from InSAR image, InSAR processing, as well as from the thermal data. If you can combine together, we have a complete environmental indicators map, which tells you this environmental impacts or the damages in these coal fields due to open cast mines, due to coal fire, and due to other kind of mining activities, including your underground mines. But underground mines, one of the major impact is the land subsidence, and that we will address separately using difference interferometric SAR technique, the later part of this session. Now you see, differential interferometric SAR, which is used for land surface displacement studies, that can be done in a conventional approach or advanced this technique. Okay, so conventionally there are at least two images you need. Okay, so between the two images, what is the phase difference? And from this phase difference, we get what is this path difference. And from this path difference, we can estimate how much the pixel has been displaced. And there are certain advantages in conventional and differential interferometric SAR that it gives you the spatially continuous measurements for a particular event. You need only one image before the event. Like, for example, if it is an earthquake, not in the case of mining-induced subsidence, like you need one image before the earthquake, another image after the earthquake. That's all. And then you generate interprogram and you will get what is the displacement due to the earthquake, isn't it? So using just a few data pairs, you can manage the show. And this processing is quite simple, much more simpler than your advanced InSAR. There are techniques like persistent scatter interferometric SAR. There are techniques like your small baseline interferometric SAR or SBAS. Okay, so this is much more simpler techniques. Interpretation also much more easier. Okay, but that is not the problem. Okay, here another thing is there are a number of post-processing algorithms available, like your summing and averaging of the interprogram stacking. Okay, then correlation rate estimation of the differential phase of overlapping interprograms, and then masking this differential phase using the correlation rate. Okay, so using these post-processing algorithms, you can overcome many of the limitations. But this limitation not to a very great extent, but to some extent only. Sometimes it gives a very good information, first-hand information, okay, as a kind of reconnaissance information. So what is recommended in many cases, hybrid approach sometimes appears beneficial, but there are many constants. Like there is the problem of spatial and temporal decorrelation. There is a problem of topographic error. There is a problem of atmospheric phase error. You need to correct it. It is possible, but you need to do that. And most importantly, it is unable to detect slow deformation in many cases. And as well as you need to have many data pairs, and very difficult to have a deformation history and time series analysis. So for a time series analysis, to get the trend, to get this nonlinear deformation component, this linear deformation component, and the residual this deformation, isn't it? This or sometimes the seasonal component, so that you won't be able to do this here. That is only possible in case of advanced InSAR technique. Now see, in case of differential interferometric SAR, this slide is important because this is the pioneering study of differential interferometric SAR, which was for the first time differential InSAR was used for getting land surface displacement measurements. It was due to earthquake. This is the Landers earthquake. So that occurred in 1992. And this in 1993, it was published in Nature, this land surface displacement due to Landers earthquake. And this is this your product was, these people came to know how the land was displaced due to that earthquake and where is the fault is located, where is the rupture located. So those things became very, very clear that there is a technique called difference interval ISRO which can do this. Okay, so similarly, this we did in the Nepal earthquake in 2015. You know, there was a 7.8 magnitude earthquake occurred. Okay, very near to Kathmandu. Okay, and then there are a lot of aftershocks. Many are above 6 magnitude aftershocks, and one of them even 7.3. This is this Kodari village, 7.3 magnitude earthquake. Now we have used this your conventional InSAR to obtain this land surface this deformation due to this Nepal earthquake. You see, this is the pattern of the displacement due to the main shock. This is the area which got uplifted because that means this your terrain surface becomes closer to the satellite. How much? 165 centimeter uplift, and northern part got subsided. That's very important because of this geometry of the fault which caused this earthquake. Similarly, this major aftershock that is on the eastern part, 140 kilometer from the main shock, the east southeast. Okay, here you see this is the affected area, and this part got uplifted and this got subsided. And this upliftment is 65, but this is along the radar line of sight, similar to the previous one. And here there was subsidence happened, which is about 35 centimeters. Now, if you want to see the totality, what is the total deformation happened due to the earthquake and the aftershocks for a period of, let us say, around 1 month or so, including the major aftershock of 7.3, this is the total displacement picture of the Nepal earthquake. Now, there are many, this large magnitude earthquake occurred. Many are above 7.5, okay, like in case of this Iraq, Iran, this in case of this number of other places, no? So that all these earthquakes, you can map the displacement, land surface displacement due to the earthquake, and sometimes even the rupture can be mapped, but in this case, no. So using this differential interval ISRO, but it is here you need only conventional differential interval ISRO, no advanced. Is your PS InSAR, persistent cutter interferometric SAR, or ISBAS is required here. Similarly, this InSAR can be used for landslide monitoring. This is an example that see there is this reservoir. This is the Terry reservoir in India, in the state of Uttarakhand. So all along the rim area, there are the slow movements of the terrain is happening. There are landslides are occurring. But before the landslide, the slow movement of the mass is happening very much, isn't it? So that we could map this all along the rim of this your reservoir. This is the from conventional differential InSAR, this L-band SAR we have used, and from that we could map this is the deformation is happening all along the rim area, and that we validated with campaign mode GNSS survey results. Similarly, this advanced InSAR we can do, though it is not for the same area, but it is the similar area, but here it is not this your reservoir, but it is a natural lake. It's a Nainital lake. You see, there are a number of areas are there. There are landslide movements are very, very important. But here, depending on your direction of the slope of the this area terrain with respect to your satellite azimuth and the node, like ascending and descending. Sometimes what is happening, you are getting this distance is increasing if the slope is opposite. Okay, for example, here it is showing uplift, whereas here it is showing subsidence. So your subsidence or uplift you are getting, it is a function of what is your satellite, your Duke direction, satellite azimuth. Okay, whether what is the satellite path means, I mean ascending or descending, and what is the direction of slope of the terrain. That is very, very important. Okay, those things need to be taken care while interpreting this land surface deformation. Okay, whether it is going along the its deformation in case of this landslide, always it is going along the slope only. It is not going up the slope. Only thing, the direction is different. In this case, for example, it is towards this direction is towards east. In this case, what is happening? It is towards west. So this direction is different. That is the reason why sometimes it is coming that distance between the satellite and the terrain is reduced, and sometimes the distance appear to be increased. But in both the cases, it is moving down the slope. Now coming to the land subsidence studies. So land subsidence, basically the lowering of the land surface due to natural and anthropogenic causes. Natural causes, there are several, like acidification, compaction and consolidation of soil and sediments, post-depositional downwarping, then slope-induced subsidence as well. But what is important to us is anthropogenic, like over-extraction of groundwater that you have listened in the previous lecture, groundwater over-extraction and land subsidence. Then extraction of petroleum, hydrothermal fluid. That is very, very important. Petroleum, oil and gas extraction, and sometimes hydrothermal fluid. So there are voids developed underneath, and that causes subsidence. And most importantly, underground mining of minerals and rocks. That is what we'll be discussing today. And underground excavation, dewatering of aquifer for tunneling, for installation of infrastructure like your metros. And it can cause different kind of damages. Some of them from India, some of them from other countries, like it is from Indonesia, some of them from Iran. Okay, then you see these different kind of damage to the terrain and to the buildings. The cracks or collapse of buildings, road and land, misalignment of the bridge, railway tracks, damage to road, railways and underground pipelines, and sometimes collapse of the oil casing. You can see what is happening. Terrain was initially here. Now the terrain has gone down this much. Isn't it? This is the oil casing you see here. Similarly here, how much it has gone down. This is in case of this Iran, Rafsanjan area, and this is in case of Bandung, Indonesia. Now see, coming to this land subsidence characteristics in case of coal fields. You know, coal fields, coal deposits are bedded deposits, and mining in case of coal fields can be done. A number of mining techniques are there. The primary mining is by board and pillar or room and pillar technique, where we make some galleries. Okay, and from these galleries, coal is taken out, mined out, and on the sides there are the pillars of coal that remain intact to support the roof. Okay, so coal pillars remain intact, and only galleries are extracted. So that in then what is happening? We have voids in the galleries. Okay, but sometimes we do the sandstone very religiously, fully packed. Sometimes it is not. So depending on what is the level of sandstone, how much compaction can be done, this deformation will vary. So here you see on the galleries, here all the mining happened by the these room and pillar techniques. So it is, you see, the area. Okay. And see here, this is in case of coal fields, this is the pioneering study was made in Poland, Silesia coal field. Okay, and in 1999, and this is the nature of this land subsidence in case of this coal mining, where the coal mining is done by this board and pillar or room and pillar technique. But if the mining is done by longwall mining technique, there is another technique where these coals are extracted in mass. In such cases, this your subsiding areas is quite extensive, wider. But this is the primary mining. Then there are secondary mining that in the next slide that we'll be discussing in Indian coal field. There mostly your mining is being done mostly in the second phase. In some cases, still room and pillar or board and pillar is being done, but in most cases it is in the second phase of mining. So first phase of room and pillar has been done. In some cases, there are longwall mining is being done. That is the primary mining. But secondary mining can be done by two approaches. One is by caving, where there is no settlement. That is this area which is there is no risk factors. Okay. So barren land. So the approach is here just to make the caving there, and this coal is taken out, and this entire land surface is allowed to collapse. So rate of subsidence will be high. And most of the areas it is not like that. It is by depillaring technique. So development and depillaring. So how it does in such cases where your remnant pillars, the first phase the galleries are mined out. Second phase pillars remain intact. So pillars are getting depillared. These pillars are taken out. And as the pillars are taken out, we need to do sand stowing. Okay, stream with sand is injected. Okay, so in such cases, your subsidence is not that high. But if this sand stowing is not done very religiously or is not feasible, in such cases, your subsidence rate is high. Now you see in this case of Jharia coalfield, you see this is the part of the Gondwana coalfields in India. That is in this your eastern part of the India. This is the Jharia coalfield, and there are many other coalfields. There are 54 Gondwana coalfields in India. So in Jharia coalfield, we have studied because it is very, very important in terms of the hosting prime coking coal, as well as it has the maximum environmental damage has happened due to subsidence and coal fire. See, we have used multi-frequency approach. In multi-frequency approach, we have used shorter wavelength C band as well as longer wavelength L band. And why it is important? Because when you use the shorter wavelength like X band and C band, because its wavelength is small, it is very sensitive to slow subsidence. So even if the subsidence rate is very slow, it is very easy to detect. But there is a disadvantage. Because the wavelength is very, very small, temporal decorrelation is very, very strong. So if the time difference is little large, then decorrelation is very high, your coherence value is very, very less, and this your information content of the interprogram becomes less and noise content is high. Okay. But in case of L band, longer wavelength, decorrelation is less, but because it is a very long wavelength, 23 centimeter wavelength, so it is sensitive to rapid subsidence. So L band is very sensitive to rapid subsidence. C and X band are sensitive to slow subsidence. Okay. In case of C band, some of the rapid subsiding areas are missed. We cannot identify because if the subsidence is very rapid, so that the phase jump between the adjacent pixels when it happens more than lambda by 2 displacement, that we cannot measure. There is decorrelation. But in case of L band, it is not happening because wavelength is very, very long. Okay. So you see here in case of C band, all the slow subsiding areas and moderately subsiding areas could be detected well from the fringes. Whereas in case of L band, only the rapidly subsiding areas we could identify well. So moderately subsiding to rapidly subsiding, not the very slowly subsiding areas. Now you see, we have prepared one subsidence map from C band, another from L band, longer wavelength, and their rate of subsidence you can see in C band we can get the subsidence rate up to 30 to 35 centimeter per year, whereas in case of L band we are getting even up to 50 to 60 centimeter per year. So total subsiding areas we mapped for the observation period. Now there is this ground-based surveying techniques are used by precision leveling and by total station survey. What are the areas which is subsiding? That is being done by the mining agencies, and this kind of map we could prepare after compiling all this information from the mining agencies, and then we compared and validated. Now you see this is the mining galleries and this mine plan. Okay, and here you see this is this conventional InSAR fringe, and followed by we have adopted this advanced InSAR like PS InSAR, but for that purpose we need large number of data. Okay, and then we can get a very precise this deformation history due to the mining. But in case of conventional this difference in informatics are there is a limitation, you know, that is the atmospheric phase. So atmospheric phase needs to be corrected. And atmospheric phase comes from the troposphere and from the ionosphere. In this case, we have shown how the atmospheric phase due to the tropospheric this phase difference can be corrected. Okay, so here are the three components are important. What is the surface pressure, surface temperature, and the water vapor that we get from these in situ meteorological observations, as well as from this satellite-based water vapor retrieval. So for that particular image pair, we have estimated these values of the surface pressure, surface temperature, and water vapor pressure. And for these two images, we have calculated that. And then from the troposphere, there are three components like your hydrostatic phase, then this weight component, and this your liquid component. Liquid component is insignificant, so it is not required. So this, what is the hydrostatic and the weight components we have estimated. And for the C band and L band, this what is the atmospheric, this your path delay that we could calculate. So this we need to correct out for each pixel. This is for the information for a particular pixel. Okay. Now, see, this is the RadarSat-2 C-band interprogram, differential interprogram, and this is after correction in blocks. Now, at the fringe level, how the refinement has happened. This is the fringe before the atmospheric correction, and this is after the atmospheric correction. Okay, so that is important. But nowadays, you can do it from the online tools. Okay, atmospheric phase correction by geckos. Now, you see, after all this displacement or this subsidence map we prepare from this the conventional and this your advanced INSAR, we need to validate it. And for this purpose, for some study sites we have fixed where we need to have the monitoring stations. For each of the study site, we have more than 30 monitoring stations we have made. And for this 30 monitoring stations, we have measured what is the X, Y, and Z. Z we have measured by this precision leveling technique, by this your leveling network, leveling benchmark existing available by the Survey of India. And this lateral displacement we have done by this campaign mode GPS survey, short duration, around 30 to 40 minutes, classical static GPS survey we did. Okay. Then the horizontal displacement we have measured from that. So horizontal we have measured from GPS. This is the GPS receiver, and the vertical we have measured from this precision leveling techniques. So for that purpose, we have worked with in multi-organizational your collaboration. Okay, this Indian Institute of Remote Sensing with Survey of India, Geodetic and Research Branch, and as well as this your Center for Mining and this Mining Research Institute. This is Center for this is the Institute of Mining and Fuel Research, in fact, CIMFAR. Okay, so all this you can validate all this lateral displacement, vertical displacement from this. You can resolve from the line of sight displacement from the INSAR, and then we have compared this labeling. From labeling, we are getting the vertical displacement of 13.6, and from the C band INSAR, we are getting 12.5, and from L band, we are getting 18 centimeter. So you can see this level of matching. Okay. Now, in case of this difference interferometry for land subsidence monitoring in hard rock mining, mostly it is by underground mining only, and it is very deeper level mining. Okay, underground deeper level mining. So because it is deeper level and it is a hard rock area. So what happens here, the subsidence rate is very, very slow, except 1 or 2 points. Subsidence rate is very, very slow in this area, not more than 2 to 3 centimeters per year. Okay, but subsidence affected area is wider. Why? Because it is quite deeper level. Okay, so it is when it is reflected at the ground surface from a deeper level, this your voids. So this affected area becomes wider. So here we have adopted 2 approaches. One is the stacking of INSAR derived LOS deformation. So you see a number of differential interprogram, okay, that we have stacked together. So it's similar to this your summing of differential interprograms. Okay, so stacking of differential interprograms. Then we could find this noise component is much more reduced, and the deformation component is much more highlighted. And this is how we have shown here. This is the areas which is undergoing subsidence. And by advanced INSAR technique like persistent scatter interform INSAR, PS INSAR, we can get it this time series deformation history, how temporarily this subsidence is happening. Okay, so you see here in some areas there are subsidence rate is high, it reaches up to 12 to 14 centimeter, but in most of the cases subsidence rate is 2 to 3 centimeter. You can see here as well, not more than 5 centimeter per year. Okay, so with this we conclude this mining induced deformation. There are other areas maybe we could discuss, but let us see what you have any queries, then we'll address if you have any questions or queries. Okay, and we'll conclude. Okay, explain from other slides. Okay, so thank you. Right.
lecture.
Okay.
Okay.
Okay.